So hello, welcome back to design of RC structural elements. So today we are going to discuss about design of doubly reinforced sections. So that is design of doubly reinforced beams. So please write down these points. I am going to discuss these points once those points are written. If the applied design moment that is due to design load is greater than the moment of resistance of a singly reinforced section, that is MU limit, so there can be three alternatives. Three alternatives. One is if possible increase the dimensions of the section preferably depth Number two, use of higher grade concrete to increase the moment of resistance of the section steel reinforcement may be added in compression zone to increase the moment of resistance of the section. That is, this is known as doubly reinforced section or doubly reinforced. Okay. See, when we are going for a singly reinforced section, there is a limit for it. So, there is a limit up to which it can resist moment. So, what is the limit? Mu limit. So, if you look at the code book on page 96, you will have a formula for mu limit. So, that is the limit up to which you can go for. Okay, that means you can apply the design load until the maximum bending moment, that is the design bending moment, maximum design bending moment reaches mu limit value. What if the moment exceeds mu limit value? That is, what if the moment exceeds due to external design load? Then these are the three alternatives we can go for. So, what is the first alternative? If possible, increase the dimensions of the section, preferably depth. So, you can increase width, depth or both. So, normally what we do is we are going to go for increasing the depth and we try to maintain the same width. Even if you increase the width, it is going to contribute to the moment of resistance of the section, but it is not going to be an increase to a great extent, okay, when compared to the depth. So, next one is use of higher grade concrete to increase the moment of resistance of the section. Of course, you can use rich concrete to increase the moment of resistance of the section. Rich concrete, FCK value increase, automatically moment of resistance of the section, that is mu limit, will go higher. But this is rarely done. That is point number 2, is rarely done. What is the next point? Steel reinforcement may be added in compression zone to increase the moment of resistance of the section. This is known as doubly reinforced. That is what we are going to do in this class. Okay. So, what we can do is, when you get a plan of a building, so what architects do is they are going to restrict the beam dimensions. Okay, they say the beam width should be this much, the beam depth should be this much, it should not increase beyond certain depth. So, those are the restrictions they are going to put. In such cases, what we do is, if we are getting the load which causes the design moment greater than mu limit, then we cannot just provide singly reinforced. Instead, we have to provide reinforcement in the bottom in the tension zone as singly reinforced section up to mu limit value, plus you need additional reinforcement in the compression zone, plus some more additional reinforcement in the tension zone to compensate whatever reinforcement we have added in the compression zone. So, this is called doubly reinforced section. A doubly reinforced section is one wherein we have reinforcement in both compression and tension zones. Is it clear to you? So, once we take up a problem, it is going to be more clear to you. Before proceeding with the problem, please write down this. I hope all of you have SP16 now, by now, from table F, page 13 of SP16. Just like IS 456, there is one more book called Special Publication 16. Okay, I hope you have the Xerox copy of that, or at least a copy of it. Okay, you have to keep that book open with you. So, I am getting the values in the table from here on this page from table F. So, for quick reference, I am going to write that d dash by d So FSC value, that is the design compressive strength of compression steel. So for this we have two types of steels. One is FE 415 and the other is FE 500. FE 500. So what if D dash D is 0.05? So D dash D, what is D dash? It is the effective cover to the compression reinforcement. So what is D? It is the effective depth. So D dash D is equal to 0.05 for Fe 415 steel. Design compressive stress is going to be 355 Newton per millimeter square. For Fe 400, 424 Newton per millimeter square. If this is 0.10, then it is going to be 353 Newton per millimeter square, and for Fe 500 steel it is 412 Newton per millimeter square, and for 0.15 it is going to be 342, and for 500 steel it is 395 Newton per millimeter square, and for 0.20 it is going to be 329 Newton per millimeter square, and for Fe 500 steel it is 370 Newton per millimeter square. So I got these values from this. So we can carry SP16 into the examination. So both IS 456 2000 and also SP16, that is allowed. So SP16 is, for your syllabus, we are going to extensively use in the design of columns. So especially the columns subjected to uniaxial bending and also biaxial bending. Okay, you must need SP16. Please write down that. So let me take up a problem. So this is from one of the examinations. A doubly reinforced concrete rectangular beam concrete rectangular beam 250 millimeter by 500 millimeter is required to support a load of 40 kilonewton per meter, including self weight. Including self weight. Effective span 5 meter. Comma, effective cover 50 millimeter, M20 concrete, and Fe 415 steel find the steel required for flexure and shear. For flexure and shear. So in the examination, this question carried 12 marks. So solution. So I am going to write the steps. So it is to calculate design bending moment and design shear force, to calculate MU limit, to calculate AST1, that is AST limit for a balanced section, to calculate AST2 and ASC next is a reinforcement curtailment. So I am going to add reinforcement curtailment to the fourth step itself. So design for shear or check for shear, design for shear and deflection, check for deflection, and finally reinforcement details. Okay. So here I'm going to go through the problem. Say a doubly reinforced concrete rectangular beam. It specifically says it is going to be doubly reinforced, of size 250 millimeter by 500 millimeter. That is, width is 250 millimeter and the overall depth is 500 millimeter. Is required to support a load of 40 kilonewton per meter. 40 kilonewton per meter is the service load. To arrive at the design load, we have to multiply this value by 1.5, which is the load factor. So including self weight. So this includes self weight already, so you don't have to add self weight once again. So effective span is 5 meter, effective cover is 50 millimeter. So effective cover 50 millimeter is for both compression and tension steel. We are going to take the same value as the effective cover. So M20 concrete and Fe415 steel, those are the materials we are using. Find the steel required for flexure and shear. Okay, you need to work only for flexure. That is, what is the tension steel required at the bottom, what is the compression steel required at the top, okay, and shear force, what are the stirrups you need to provide, at what spacing, etc. Only that much you need to do. After that, you need to show the details under reinforcement details. However, for the sake of completeness, so what I am doing is I am checking for deflection as well. So in the examination for the same problem, you don't have to check for deflection, but here I am going to do the same. I am going to do the deflection check for the sake of completeness. Okay. So, let us go with the first step. So, first is to calculate the design moment and to calculate design bending moment, design BM, that is bending moment, and the design shear force. So, load given is like this is service load, total service load. I am going to call that as W, that is equal to 40 kilonewton per meter. Therefore, design load, I am going to call that as WUD, load factor of 1.5 multiplied by 40, that is equal to 60 kilonewton per meter. Okay. So, what is the span given? The span given is 5 meter, that is the effective span. I am going to make use of this value for all calculations. So, this is 60 kilonewton per meter. So, this is 5 meter is the span. Okay. Therefore, design bending moment, design BM, that is bending moment or simply moment, MUD equal to WUD LE square by 8, where LE is this, that is the effective span. So, WUD is 60 multiplied by LE square is 5 square divided by 8. Okay. 7.5, the value is 187.5 kilonewton meter, that is equal to 187.5 kilonewton meter is the value of MUD. Okay. And design shear force, design shear force is VUD equal to WUD LE by 2. So, that is equal to 60 multiplied by 5 by 2, that is equal to 150 kilonewton is the design shear force. Okay. That is VUD value. So, this is done and this is done. What is the next step? To calculate MU limit. Hope this is complete. Next is to calculate MU limit. So, that is nothing but what is the maximum moment a singly reinforced section can carry by being this one, a singly reinforced and by being maintaining the same dimensions. Okay. So, from the code book, that is from 1.1c page 96 of the code book, MU limit equal to 0.36 XU max by D 1 minus 0.42 XU max by D and FCK BD square. This is the formula we have. So for XU max by D, I am going to substitute 0.48. Okay. So where do we get this value from? We are going to get this value from page number 70 of the code book. So that is, if you open page number 70, again you have done it so many times already. So you are going to do it once again. For Fe415 steel, it is 0.48. So 0.36, this is 0.48. 1 minus 0.42 into 0.48. FCK is M20 concrete. What is B? B is this dimension. So B is 250 millimeter. And what is D? Small d. That is the effective depth. This is capital D. And if you take out effective cover of 50 millimeter from the overall depth, you are going to get the effective depth of 450 millimeter. So here I am going to write 450 square. So mu limit equal to mu limit equal to 139.69. 69 into 10 to the power of 6 Newton millimeter, that is equal to 139.69 kilonewton meter. This is mu limit. Okay. See, being single reinforced, the beam can carry a maximum bending moment of 139.69 kilonewton meter. But what is the maximum bending moment we are getting due to design load? That is equal to this value. I forgot to write that value. That is 187.5 kilonewton. That is, it's already there, 187.5 kilonewton meter. Okay. So the difference between this and this will have some value. So that should be taken care of. How do you take care of that part? So you are going to take care of that part by providing some reinforcement in the compression zone, and to balance that compressive force in the compression zone due to the reinforcement, we are going to put additional reinforcement in the tension zone. Is it clear to you? So this is 139.69, this is greater than MUD of 187.5. Therefore, we have to go for doubly reinforced section. Doubly reinforced section. So the next step is 3. So to calculate AST1, that is AST limit for a balanced section. for a balanced section. So if the section is balanced, okay, that balanced section carry or withstand a maximum design resisting moment of 139.69 kilonewton meter. Is it clear to you? So to calculate AST1 for a balanced section, again if you open page number 96 of the code book, so by equating compression force with the tension force, so what we are going to get is from 1.1a, 1G 1.1a, page 96, we have XU by D equal to 0.87 FYAST divided by 0.36 B FCK D. B FCK D. Okay. So this is the formula we are going to make use of. For a balanced section, XU by D becomes XU max by D, that is equal to 0.48. Okay, of course from page 70 of the code book. And AST becomes AST limit, that is nothing but AST1 value. So by substituting these values in this equation, we are going to get 0.48 equal to 0.87415 into AST limit divided by 0.36, B is 250 and the depth is 450 and M20 concrete. So FCK is 20. Therefore, AST limit equal to 1076.86 millimeter square. That is nothing but AST1 equal to 1076.86 millimeter square. So please draw this figure. Let me write it later. To calculate AST2 and ASC. That is the next step. Hello. The next step is to calculate AST2 and ASC. So that is to calculate AST2 and ASC. So please write down this figure. So this is the final section with the reinforcement. This is ASC, that is reinforcement in compression zone. This is AST2. This is AST1. Okay, and this beam is having a width of 250 millimeter and a overall depth of 500 millimeter and an effective depth of 450 millimeter, because the effective cover is 50 millimeter. So 50 millimeter effective cover for the tension steel and also 50 millimeter effective cover for the compression steel. This is 50 millimeter. Okay. So we have calculated this AST1, that was 1076.86 millimeter square, that is AST1 equal to 1076.86 millimeter square. Okay, and this area is good enough to take care of the moment of magnitude 139.69, that is MU limit value, 139.69 kilonewton meter. Okay, so what is the design bending moment? Design bending moment is 187.5 and MU limit is 139.69. So we will do the calculation and we will find out what is the moment to be carried by additional tension steel and compression steel. So design bending moment MUD equal to 187.5 kilonewton meter. So for the section of this size, MU limit was 139.69. Therefore, moment to be, that is the design moment to be carried, or design bending moment to be carried by the additional reinforcement. I am going to call that as MUD2 equal to 187.5 minus 139.69. So that is equal to 47 and 0.81 kilonewton meter. That is MUD2 equal to 47.69 kilonewton meter. Okay, and this is the distance between the centroids of compression and tension steel, that is 500 minus 2 multiplied by 50, that is equal to 400 millimeter. Okay, so finally if you combine these two, so we are going to get the reinforcement, total reinforcement here in the compression zone and some reinforcement in the tension zone. So this is again 250 millimeter, this is 500 millimeter, that is capital T, and this is B. Okay. So additional reinforcement MUD2 47.81, that is 47.81 kilonewton meter, and this reinforcement to be carried by these two steel areas. So what we do is we are going to put some reinforcement in the tension zone, and to neutralize that, or to this one, to equate that, we are going to put some compression reinforcement to balance compression and tension. So here we should not use any concrete area in the compression zone, because that is already considered to take care of the moment of 139.69 kilonewton meter. Is it clear to you? Next, going further, what I can, moment of resistance of the resistance of the section equal to that is total tension divided by the lever arm. Okay. So what is the total tensile force? That is 0.87 Fy, that is the design tensile strength of steel multiplied by the area of steel AST2, that is 0.87 Fy AST2 multiplied by the lever arm. So that is the distance between the centroids of these two steel areas, that is D minus D dash, where D dash is the cover, the effective cover for the compression reinforcement. Here D dash equal to 50 millimeter, here also it is 50 millimeter for the tension reinforcement. Okay. So I repeat, whatever the applied moment due to the design load is going to be resisted by the moment of resistance. That moment of resistance is offered by the compression steel and the tension steel, and this compression steel develops compressive force and this steel develops tensile force, and those two forces are of the same magnitude to maintain force equilibrium, and those two forces are opposite in nature. One is compression and the other is tension, and these two forces are separated by certain distance, that is this one, D minus D dash. So as a result they are going to form a couple, that is the moment of resistance, and the moment of resistance value is given by 0.87 Fys to D minus D dash. So in place of moment of resistance of this section, we are going to substitute 47.89 kilonewton in Newton millimeter, that is 47.89 into 10 to the power of 6, that is equal to 0.87 into Fy is 415 steel multiplied by AST2. So what is D? That is 450 minus 50. Therefore, AST2 equal to 331 millimeter square. What it means? We need 331 millimeter square area of tension steel to resist the bending moment of design bending moment of 47.89 kilonewton meter. Okay, to balance this tensile force we need to add compressive force. To take care of the compressive force we need some compression reinforcement. Okay, we need to find out what is the area of compression reinforcement required. So next what I do is, by equating total compression to total tension, we get what is total compression? Area of compression steel ASC multiplied by stress developed in compression steel. That gives a force that should be equal to area of tension steel AST2 multiplied by 0.87 Fy. Okay, and this is the design tensile strength of the steel. See, here I am using 0.87 Fy, here I am using FSC value. So for 415 steel, if I take 0.87 Fy, 0.87 into 415 is equal to 361 Newton per millimeter square. So the steel is going to develop this value under tension. It's not a problem. When it comes to the compression, the steel is not going to develop this much because it is under compression, so there is likely chance of the reinforcement getting buckled. So as a result, so the buckling stress in the steel in the compression zone will be less than this value. So we need to get what is that FSC value. So we know everything in this side, and we need to know what is FSC. Once we know FSC, we can find out what is ASC value required. So to find out FSC, if you, in the same problem in the beginning, I gave you the table. Okay, that is on table F, page 13 of SP16. Okay, you have different FSC values for Fy equal to 415 and for Fy equal to 500 depending on the values of D dash by D. So what is D dash by D? D dash is the effective cover for the compression reinforcement and D is the effective depth. So first we will find out what is D dash by D. So before going further, let me call this as equation A. Okay. So to find out FSC from table F, page 13 of SP16, D dash by D value and FSC value in Newton per millimeter square. Okay. So before that we need to find out what is the actual D dash by D. Okay. So I am going to find out so D dash by D equal to 50 millimeter, 450 millimeter, that is equal to 0.11. Okay. So if you look at the table given in SP16 for 0.10 value, it is 353 Newton per millimeter square, and for 0.15 it is 342 Newton per millimeter square, and ours is 0.11. So what is the value? Okay. So let us find out what is the FSC value corresponding to the value of D dash by D through linear interpolation. Therefore, FSC value equal to 342 plus, so that is 0.15 minus 0.10, then 0.15 minus 0.11, and 353 minus 342. Therefore, FSC equal to 350.8 Newton per millimeter square. Okay. So by substituting the values in equation A, we get. So ASC we don't know, we need to find out, and FSC value is 350.8. That is equal to AST2 we have calculated already, so that was 331 multiplied by 0.87 into 450. Therefore, ASC equal to 340.67 millimeter square. Okay. So once this is done, total area of tension steel AST equal to AST1 plus AST2. What is AST1? That was 1076.87 plus AST2 is 331. Okay. So it is 1407.87 millimeter square. That is AST. And ASC equal to 340.67. Okay. Now I can write here AST2, this is AST1, this is AST2 equal to 331 millimeter square, and this ASC equal to 340 millimeter square. So if you add this compression area and this compression area, here we have 0. So we get total reinforcement in the compression zone, and if you add AST1 and AST2, so we are going to get the total area of reinforcement in the tension zone. So here I am not going to put AST1 plus AST2 value here and ASC value here. No. First, I am going to find out how many bars I need. Then I am going to put those bars over there in the final figure. So let us use 22 mm dia bars in the tension zone. Okay, that is basically tensile steel. Okay. Therefore, number of 22 mm dia bars equal to, so what is the total area of tension steel? That is AST, area of each bar, that is equal to, what is AST value? 1407.8 divided by pi by 4, 22 square, that is equal to 3.70. Okay? Say 4. Say 4. Therefore, we shall provide 4 bars of 22 mm dia. Okay? Similarly, and let us use 16 mm dia bars in the compression zone. Okay? Therefore, number of 16 mm dia bars equal to, that is total area in the compression zone, that is ASC, area of each bar, that is equal to 340.67 divided by pi by 4, 16 square. So I am going to get, I think, 1.69, say 2 bars. Okay? Therefore, we shall use, or we shall provide 2 of 16 mm dia bars in the compression zone. So once this is done, show the reinforcement numbers here. So this is 4 of 22 mm dia. This is 2 of 16 mm dia. Okay? So this completes. What is the next thing? We need to check for AST minimum and AST maximum. So I am going to write that part and I am going to leave some space. Okay? And you do it yourselves, because I have done it already so many times, so I don't have to repeat it and I don't want to repeat it. Check for AST minimum, formula, that is AST minimum equal to 0.85 Fy divided by Bd. So check it. Similarly, check for AST maximum, that is 0.04 Bd, where D is the capital letter. Okay? So once you do this, compare these two values with the actual area of steel provided, that is 4 multiplied by pi by 4, 22 square. Okay? So make sure that value falls between AST minimum and AST maximum. If the value, as I said in the previous classes, falls below AST minimum, go ahead and provide at least this much. Okay? And if AST actual value exceeds AST maximum, then whatever the sectional dimensions you have given is adequate, go back and redesign the section and repeat the design from the beginning. Okay? So this completes this step, except one thing, that is regarding development length. Next is to check for development length. I am including the development length check and also curtailment of reinforcement within this step itself. that is curtailment of reinforcement. Curtailment of reinforcement. So this is the beam. This is one of the supports. Of course, support width is not given in the problem, and we are going to take here, that is the center of the support, to the center of the support on the other end as 5 meter, because that is given in the problem. And we are providing tension reinforcement in the tension zone, that is 4 bars of 22 mm dia, 22 mm dia. See, as I discussed in one of the previous problems, so we can curtail 2 bars, that is 50% of the bars, where we have 50% bending moment, 50% of the maximum bending moment. So that is available at a distance of L by 7. Okay, L effective by 7, where LE equal to 5 meter. Okay. So theoretically you can cut off 50% of the bars at a distance of LE by 7 from the center of the support. However, the code says from the theoretical cutoff point, the bar should be extended for a distance of 12 times the diameter of the bar or 1 effective depth, whichever is greater. Okay, extend that bar to that length. There, cut the bar. Or if you have too many bars, you can just crank the bars, that is bend the bars, and you can make use of that bent up bar for shear. That can be done. Okay. So please do that part from your side. I am not going to do this. Okay. Practice that part. Practice that part. Next, it is check for shear. Check for shear. So, check for shear. This is the beam of span, effective span 5 meter, and the design load WD is 60 kilonewton per meter. Okay. So what is the reaction? That is 60 multiplied by 5 divided by 2, that is VUD equal to 150 kilonewton, and here also it is VUD equal to 150 kilonewton. Okay. So design shear force VUD equal to 60 multiplied by 5 divided by 2, that is equal to 150 kilonewton. Okay. So nominal shear stress, therefore nominal shear stress tau V equal to VUD divided by BD. So what is VUD? That is 150 kilonewton. Convert that value into Newton, divided by B is 250 and the effective depth is 450. Okay. So tau V equal to how much? It is 1.33 Newton per millimeter square. Okay. So that should be less than tau C max. So for M20 concrete, from table 20 on page 73 of the code book, tau C max is how much? 2.8 Newton per millimeter square. Therefore, no redesign of the section is required. No redesign of the section is required. So if this exceeds 2.8, go ahead and redesign the whole section, that is increase the dimensions of the section. Okay. So once this is done, the next step is to find out the shear capacity of concrete. Okay. So from the shear capacity of concrete, this minus the shear capacity of concrete will give you the shear force to be carried by the stirrups. So to find out the shear capacity of concrete, so first thing we need to do is we need to find out what is the percentage of tension steel at the support. So here at the support we have 2 bars of 22 millimeter diameter. So of course in the mid section where we have maximum bending moment, we have provided 4 of 22 millimeter diameter. As we come towards the support, bending moment reduces. So as a result, we have curtailed 2 bars. So at the support, we are left with only 2 bars. So find out the percentage of the tension reinforcement at the support. Okay. Therefore, VUD equal to VUC plus VUS. So I'm going to call this as equation B. See, the total shear force to be carried by concrete and the remaining shear force to be carried by steel. In this case, steel is bent up bars and stirrups. So we are not providing any bent up bars here. So the remaining shear should be carried by the stirrup. Let us go and find out what is the value of VUC first. So that is VUC equal to what? The first thing we need to do before you find out VUC is to find out tau C. Okay, that is the design shear strength of concrete. So go and refer table 19 on page 73 of the code book. Okay, find out what is tau C. Tau C depends on the grade of concrete and also percentage of tension reinforcement at the support. Let us find out what is the percentage of tension reinforcement at the support. That is percentage of tension reinforcement at support equal to 2 bars of 22 millimeter dia multiplied by BD, that is 250 multiplied by 450 is the effective depth multiplied by 100. So that is equal to 0.66% is the value of the tension steel, that is the percentage of tension steel. So again from table 19 page 73 for M20 concrete, percentage of steel, that is AST by BD multiplied by 100 and tau C value, that is the design shear strength of concrete. So for 0.5 it is percent, it is 0.48 Newton per millimeter square. For 0.75 it is 0.56 Newton per millimeter square, and for 0.66, so what is the value of tau C? Therefore, tau C value equal to 0.48 plus 0.75 minus 0.50 divided by, dash 0.66 then it is 0.56 minus 0.48, that is equal to tau C equal to 0.53 Newton per millimeter square. That is the design shear strength of concrete. Okay. Therefore, design shear capacity of concrete, or simply shear capacity of concrete, is VUC equal to tau C BD, that is equal to 0.53 multiplied by 250 multiplied by 450, divide that value by 1000, VUC equal to 59.63 kilonewton. See how out of the design shear force of 150 kilonewton, so the concrete is going to take care of this, that is 59.63 kilonewton. Okay, then substitute this value here, then we are going to get the value of VUS, that is the value to be taken care by the stirrups. Therefore, by substituting the values in equation B, we get, for VUD I am going to substitute 150 equal to, for VUC it is 59.63 plus VUS. Therefore, VUS equal to 90.37 kilonewton. Is it clear to you? 90.37 kilonewton. So that is the shear to be carried by the stirrups. So now the design to be carried by stirrups is 90.37 kilonewton. So let us use 8 mm dia 2-legged stirrups. 2-legged stirrups. Therefore, spacing of stirrups is SV equal to 0.87 FY ASV D divided by that is VUS, that is the shear force to be carried by the reinforcement. Reinforcement means bent up bars and stirrups. Here we are not providing any bent up bars, that is why whatever the shear force, remaining shear force should be carried by the stirrups. So that is 0.87 into 415 multiplied by 2-legged 8 mm dia stirrups, and the depth is 450 millimeter, divided by VUS is 90.37 multiplied by 1000. Therefore, SV equal to through calculation I got the value equal to 180.7 millimeter center to center. So that is the spacing. However, the spacing should not exceed the following three cases. So check for maximum spacing. That is, what is the maximum spacing up to which we can go? As per the codal recommendation, the spacing should not exceed 0.75 times D, that is equal to 0.7 times. So D is 450, that is equal to 337.5 millimeter, and in no case it should exceed 300 millimeter center to center. Okay, and also it should not exceed, the spacing should not exceed 0.87 Fy ASV divided by 0.4 B, that is equal to 0.87 415 into 2 multiplied by pi by 4 into 8 square divided by 0.4 times 250, that is equal to 363 millimeter center to center. So we have four values. One is 180.87, that is as per the calculation to carry the shear force of 90.37 kilonewtons. So that is, another is 337.5, 363 and 300. So take list of these three values, of these four values. Therefore, spacing of 8 mm dia 2-legged stirrups equal to 180 millimeter center to center. Okay, this is the shear reinforcement we are going to provide. So after this, next step is check for deflection. Check for deflection. So for a simply supported beam, the deflection condition is generally satisfied if LE divided B is not greater than 20 multiplied by modification factors. Modification factors. Okay, that is nothing but 20. Here we are going to give modification factor due to the tension reinforcement, and also we are going to multiply this value by the modification factor due to the compression steel. So this is nothing but LE by D should be less than 20 multiplied by FT multiplied by FC. So we need to find out what is FT and what is FC. LE is known, that is 5 meter, D is the effective depth, which is 450 millimeter. So let us find out Ft and Fc. So let me call this as equation say 1. So to find Ft, so what is the percentage of tension reinforcement at this section where we get the maximum bending moment? Of course, we have provided 4 bars of 22 millimeter diameter, okay, in the tension zone. Therefore, percentage of tension reinforcement equal to 4 bars pi by 4 22 square divided by 250 multiplied by 450 and multiplied by 100. That is equal to 1.35%. 1.35% of tension steel. And Fs equal to 0.58 Fy, area of tension steel required divided by area of tension steel provided, that is equal to 0.85 into 415. So what is the value required? So 1407.86 is the required total tension steel. Okay. So what is the area of steel provided? So we have provided 4 bars of 22 millimeter diameter and the area provided is 1520.23 millimeter square. Therefore, Fs equal to 223 Newton per millimeter square. Newton per millimeter square, that is Fs value. Now look at the figure 4, that is look at the graph given in figure 4. So from figure 4 of page 38 of the code book, so Ft equal to for 1.35% of tension steel and for Fs equal to 223 Newton per millimeter square. So modification factor Ft equal to factor Ft equal to 1. Okay. Next, here we have compression steel as well. So to find out Fc value, that is the modification factor due to the presence of compression steel. So the first thing we need to do is we need to find out what is the percentage of compression steel provided. Therefore, percentage of compression steel provided equal to pi by 4 16 square, multiply that by 2 because we have provided 2 bars of 16 millimeter diameter. Okay. So divided by, so it is 250 multiplied by 450 is the effective area multiplied by 100, that is equal to 0.36%. That is the percentage of compression steel provided. And the next is, so So from figure 5, page 38, please open, because we are referring that graph for the first time. Please open it. Figure 5 on page 39 of the codebook. It says modification factor for compression reinforcement. So the value, the percentage of compression reinforcement is 0.36%. So corresponding to 0.36%, okay, if you look at the modification factor, that modification factor I have called that as FC. So FC value equal to 1.1. So FC equal to 1.1. Okay. Therefore, what is the formula we have? LE by D should be less than or at most equal to 20 multiplied by modification factor due to tension steel and modification factor due to compression steel. So what is LE by D value? LE by D equal to, LE is 5 meter and D is the effective depth, okay, that is 450 millimeter. So this should be in millimeter as well, okay, that is equal to 11.11. And so 20 multiplied by FT multiplied by FC equal to 20 multiplied by 1.1, sorry, 1 multiplied by FC value is 1.1, that is equal to 22. So substitute these two values in this equation. Therefore, 11.11 is less than 22. Therefore, deflection condition is satisfied. Is this clear to you guys? Okay. So once this is complete, check for deflection. The next one is reinforcement details. Reinforcement details. This is 5 meter or 5000 millimeter. Okay, when you are showing everything, reinforcement details in a drawing sheet, everything should be expressed in millimeter. So when you are showing reinforcement details, it is enough if we show only 50%. I'm writing the whole thing, so you can do both ways depending on the time availability in the examination. So I'm providing stirrups as per the design. So when it comes to the stirrups, yes, according to our calculation, the spacing has come to 180 millimeters center to center. As we move towards the center, certain length at the center, we can increase the spacing. The reason is, as we move towards the center, the shear force decreases. Okay? As a result, so every shear, all the shear will be carried by concrete at certain section. Where exactly it carries, you need to find out through the calculation. So between those two sections where the concrete is good enough to take care of shear without needing any stirrups theoretically, so what we can do is we can provide nominal shear reinforcements as per the codal recommendation. So what are the nominal shear reinforcements? Of course, we have to provide two-legged stirrups, at least two-legged, and 0.75 times D, 300 millimeter, and also the spacing as per the calculation given in the formula. So out of those three values, take the least value and provide that spacing between those two distances wherein the shear is less. As a result, we can save the material on stirrups. However, here I am providing the stirrups at the same spacing throughout. So that can be done, that can be calculated, where exactly we can increase the spacing of stirrups. Here, because of lack of time and also it involves little bit of additional calculation, so I am skipping that part. So if you are interested to know how it is, so by knowing all these things, you can refer any textbook. Okay, there you can learn it, or if you don't understand that, you can always come to me if anybody is interested, and I will tell you how to do it. Okay, so this is the reinforcement details. So I am going to take a section here. I am going to call this section as AA. Okay, and I am going to take one more section close to this support. I am going to call this as section BB. So section AA, what I see? I see two bars of 16 mm, 4 bars of 22 millimeter diameter, and of course stirrups provided at a spacing of 18 millimeter center to center. Okay, so this is section AA. And if I take section BB, I have curtailed 2 bars. So here in the compression zone, I am going to see 2 bars of 16 mm. In the tension zone, I see 2 bars of 22 millimeter diameter. Okay, this is section BB. So overall dimension is 250 millimeter, and overall here overall width is 250, overall depth is 500 millimeter, and the effective cover for compression reinforcement is 50 millimeter, and also the effective cover for the tension reinforcement is 50 millimeter. So these are two bars to 16 mm dia bars. Same thing here. Okay. So these are 4 of 22 millimeter dia. This is 2 of 22 millimeter dia, and these are the stirrups. 8 mm dia 2-legged stirrups. At 180 millimeter center to center. Again coming here, so it is 2 of 16 mm dia. This is 4 of 22 millimeter dia. These are the stirrups. So 8 mm dia, 2-legged stirrups at 180 millimeter center to center. Is it clear to you? Then if you come here, we have 2 bars. Two of 22 millimeter diameter, and they are continuing into the support. Okay, at what distance we are going to curtail the bars? We are going to curtail the bars at a distance of 280 millimeter from the center of the support. So same thing here, that is on both sides 280 millimeter. That is a point of curtailment. So this is longitudinal section. Okay. So this is cross section at AA, and this is cross section at BB. So please write down this figure. So this completes this problem. So next what I do is I am going to write down some problems so that you can practice. This is from one of the examinations. I hope this is complete. Please write down this problem. A concrete beam has 350 millimeter breadth and 700 millimeter effective depth. Design the beam if it is subjected to a superimposed bending moment of 400 kilonewton meter. Use HYSD bars of FE 415 grade and concrete of M20. So take D dash equal to 50 millimeter. Okay, this question carried 12 marks. So write down, let us go through this problem and I am going to explain this problem briefly. See, a concrete beam has 350 millimeter breadth and 700 millimeter effective depth. Design the beam if it is subjected to a superimposed bending moment of 400 kilonewton meter. So use the HYSD bars of FE 415 grade and concrete of M20. Take D dash, that is the effective cover for both compression and tension steel, equal to 50 millimeter. See here, superimposed bending moment. They have not given any span, they have not given any load, they have not given any shear force. You need to worry about only the reinforcement for flexure. Okay, you provide tension reinforcement, and if it is a doubly reinforced section, you need to provide additional tension reinforcement. To balance that, you need to provide compression reinforcement. So this is superimposed load. What is the design moment? So the design moment is 1.5 times 400, that is equal to 600 kilonewton meter, that is MUD value. The first step you need to do is, you need to find out what is the MU limit using the formula given on page number 96 of the code book. Let me XU max by D within brackets 1 minus 0.42 times XU max by D multiplied by FCK BD square. So using that, find out MU limit value. If the if MU limit value is less than 600 kilonewton meter, then what you have to do is up to mu limit value, find out the area of steel required to put in the tension zone. That area of steel, we are going to call that as AST1, that is same as AST limit. Is it clear to you? So once that is done, so deduct mu limit value from 600 kilonewton meter. So whatever the remaining moment you are left with, to take care of that part, you need to provide compression reinforcement, and to balance the compression reinforcement, you need to put some additional tension reinforcement in the tension zone. Okay? So once you find out the areas of reinforcements, so for this problem, you can stop once you find the areas, or else you can go ahead and provide number of bars. So in compression zone, if you assume 16 millimeter diameter bars, for example, or 18 millimeter diameter bars, so whatever AC value, that is a compression steel area required, divided by area of each bar, will give you the number of bars. Okay, round that value to next higher value. Next, similarly, area provided in the tension zone, area of steel provided in the tension zone divided by area of each bar will give you number of bars to be provided in the tension zone. So show that in the cross section of dimension 350 millimeter by 700 millimeter effective depth with 50 millimeter effective cover, the overall depth is going to be 750 millimeter. Okay. Show the reinforcement, that is tension reinforcement and compression reinforcement. So that is the end. Okay, that's what you need to do for this problem. Is it clear to you? So with that, I am going to go with next problem, that is the second problem. Okay, I am going to write down that. That is number 2. A rectangular RC beam, again this is from one of the examinations. A rectangular RC beam section 230 millimeter by 450 millimeter overall size, it is reinforced with four numbers of 20 millimeter diameter in compression at an effective cover of 40 millimeter. Determine the area of tension reinforcement. Determine the area of tension reinforcement needed to make the beam section fully effective. Calculate the maximum UDL maximum UDL, that is uniformly distributed load, the beam can carry over an effective span of over an effective span of 5 meter. This question carried 10 marks. Okay. So then how do you approach this problem? So let me go through this problem. A rectangular RC beam section 230 millimeter by 450 millimeter overall size. So it is reinforced with 4 numbers of 20 mm diameter in compression zone. Okay, not a tension zone. Instead, we are providing the reinforcement in compression zone at an effective cover of 40 millimeter. So determine the area of tension reinforcement needed to make the beam section fully effective. So calculate the maximum UDL the beam can carry over an effective span of 5 meter. So the first thing you need to do is you need to find out AST1, that is AST limit. That is for a balance section. Okay, by equating total compression to total tension. Total compression in concrete to total tension in the steel in the tension area. Okay, by using that you can find out what is the value of AST limit. You can call that value as AST. Then we have some compression reinforcement, 4 of 20 millimeter diameter. So to compensate for this or to balance this, we need some additional tension reinforcement. You find out by equating the compressive force in the compression steel to the tensile force in the tension steel, where the area of tension steel will be AST2. Is it clear to you? Find out what is AST2. So once you have it, find out the moment of resistance, that is the design moment of resistance of the section. So that is MUD equal to MU limit value plus total compression, that is stress in compression steel, multiplied by the lever arm. Lever arm is D, effective depth, minus D dash, where D dash is the effective cover for the compression reinforcement. So once you have the design bending moment, okay, let WUD be the design load coming on the beam of span 5 meter. Find out what is the maximum bending moment. Oh, maximum bending moment is WL square by 8, where W is WUD here. So once you have the maximum bending moment in WL square by 8, equate that value to design bending moment, that is moment of moment of resistance of the section. So find out what is WUD. Once you have WUD value, divide that value by 1.5. 1.5 is the load factor. So once you divide that value by the load factor, the value you are going to get is the maximum service load you can apply over the beam. Service load or working load. So what is the question here? Look here. Calculate the maximum UDL the beam can carry. Maximum UDL means, when they say maximum UDL, that is the service load. Is it clear to you? Thank you. This completes the doubly reinforced section. Thank you.